Some initial attempts at defining efficiency. The first major question we need to answer is the following. How should we turn the fuzzy notion of an efficient algorithm into something more concrete? The first attempt at a working definition of efficiency is the following. Propose the definition of efficiency. 1. An algorithm is efficient if, when implemented, it runs quickly on real input instances. Let's spend a little time considering this definition. At a certain level, it's hard to argue with one of the goals at the bedrock of our study of algorithms is solving real problems quickly. And indeed, there is a significant area of research devoted to the careful implementation and the profiling of different algorithms for discrete computational problems. But there are some crucial things missing from this definition even if our main goal is to solve real problem instances quickly on real computers. The first is the omission of where and how well we implement an algorithm. Even bad algorithms can run quickly when applied to small test cases on extremely fast processors. Even good algorithms can run slowly when they are coded sloppily. Also, what is a real input instance? We don't know the full range of input instances that will be encountered in practice, and some input instances can be much harder than others. Finally, this proposed definition above does not consider how well or badly an algorithm may scale as problem sizes grow to unexpected levels. A common situation is that two very different algorithms will perform comparably on input of size 100. Multiply the input size tenfold, and one will still run quickly, while the other consumes a huge amount of time. So, what we could ask for is a concrete definition of efficiency that is platform independent, instance independent, and of a predictive value with respect to increasing input sizes. Before focusing on any specific consequences of this claim, we can at least explore its implicit high-level suggestion that we need to take a more mathematical view of the situation. We can use the stable matching problem as an example to guide us. The input has a natural size parameter n. We could take this to be the total size of the representation of all preference lists, since this is what any algorithm for the problem will receive as input. N is closely related to the other natural parameter in this problem. Little n, the number of men and the number of women. Since there are two n preference lists, each of length n, we can view capital N, the natural size parameter n, equals to 2 times n squared, suppressing more fine-grained details of how the data is represented. In considering the problem, we will seek to describe an algorithm at a high level and then analyze its running time mathematically as a function of this input size n.